So now that we've defined a formula for the washer method, let's look at a few examples on how we could execute this. So in the first example, we're asked to consider the region bound by y equals x squared plus 1 and y equals x plus 3. And then we're going to find the integral. So really all we need to do is just set up the integral in this case to find the volume if we rotate it about the x-axis. So let's get a little sketch together and draw the cross section like we normally do. So sketch and cross section. So if we were to draw these curves, so here's our y-axis and our x-axis. Now x squared plus 1, that's just a parabola centered at the origin that's been shifted up 1 unit. So this one will be relatively easy to graph. So this is y equals x squared plus 1. And then x plus 3 is a linear function with a slope of 1 that has a y-intercept of 3. So if we were to draw that curve, then again, I don't think I'll have this perfectly to scale, but hopefully you guys get the idea. This is going to be y equals x plus 3. So here's our region that we're considering, and now we've got to think about how we could set this integral up to find the volume if we took this area that we're filling in right here and rotated it about the x-axis. So that's our other piece of information in our sketch, is to do this. And let's also, while we're here, let's draw our little cross section. So this would be a little sliver of area at some point x that we'd be rotating around. All right, so now that we've got a sketch and we know that we're going to be using the washer method here. And this is because there is a gap between the axis of rotation and the area. So since there exists a gap between that cross section and that area, we know that we're going to have to use the washer method. So if we were to move on to our next quantity that we need, which are the bounds, as we've been doing before, we're going to take, in order to find where these two curves intersect, we're going to set them equal to each other. So we take x squared plus 1, we'd set it equal to x plus 3. This is just going to be a quadratic equation, so if we set it equal to 0, then we are going to get x equals, so we can use a quadratic formula or factor this. Either way, we're going to get x equals -1 and x equals +2. So now we can mark those down. So that's going to be x equals -1, and then this point right here is going to be x equals -2. Okay, so now we need to determine, in this case, our radii, because we've got a washer method on our hands. So for the outer radius, now the outer radius is going to be the curve that is furthest away from the axis of rotation. So this is going to be the farthest from the axis of rotation. In this case, that would be r of x equals, the curve that's furthest away from the axis of rotation is going to be x plus 3. And our inner radius is going to be nearest the axis of rotation. And on this interval, now notice they change, but on this interval, the curve closest to the axis of rotation is the x squared plus 1. So here our inner radius would be little r of x equals x squared plus 1. So armed with this information, we can now go ahead and we can set up our volume. So volume is going to be equal to the integral from -1 to +2, our bounds, and then that's going to be pi times our outer radius squared minus our inner radius squared, and then integrated with respect to x. So in terms of the setup, that's all that we needed to do. So again, this is our outer radius, big R of x. This is our inner radius, little r of x.